Experiment objectives. 1. To get the velocity distribution across the open channel section. 2. Calculating the discharge using measured velocities. 3. Comparing the calculated discharge with the measured one. Experiment setup and tools. 1. Armfield Laboratory Flume. The flume is shaped as a rectangle with glass sides and a bed made of steel. The flume has a total length of 10 meters and bed width B equals 30 centimeters. 2. Point gauge. Point gauge is used to measure the bed and water levels. How to read level. 1. Where is the zero line defines the integer part of the number. 2. When two lines from right and left rulers are horizontal with each other, then the count of the right line is the decimal. 3. Tailwater gate. Tailwater gate is used to control the tailwater in the flume, increase the depth to be more than the normal depth. 4. Pumping system. Consists of the pump body, pump motor and control valve. The control valve controls the rate of discharge. 5. Orifice meter. Orifice meter is used to measure the rate of flow. How to use. 1. Measure the difference between the two tubes H. 2. From curve get Q in units of liters per second. 6. Electromagnetic flow meter is used to measure the velocity of the passing discharge. It measures the flow velocity and its inclination angle from the flow main direction. Thus, the velocity component in the direction of the flow should be calculated as shown. In order to minimize the error, velocity is measured several times, 25 times, and the device calculates their average as shown in the following equation. The following photo shows how to obtain data from the device. Experiment procedures. 1. Open the inlet valve to get a suitable discharge flowing into the flume. Measure the discharge using the orifice meter. 2. Adjust the tailwater gate to have an average water depth of 35 centimeters to have a large enough cross-section area in order to divide it easily, as will be discussed in step number 4. 3. Wait to reach the steady state, and then measure the water depth at a section near the middle of the flume using the point gauge. Then place the current meter at the measured section to start measuring the velocities. 4. Divide the section into 3 columns. Each column is divided into 4 strips. Note the equation for the strip area calculation. 5. Place the current meter's measuring disc in the middle of each strip and record the average velocity from the screen after the 25-sec count is finished. 6. Plot on the same plot the vertical velocity distribution for each column. 7. Plot on the same plot the horizontal velocity distribution for each row. 8. Plot the velocity contours on the cross-section. Same velocities are connected with same line. 9. Calculate Q corresponding to the measured velocities at each strip. Then, compare it with the measured one from the orifice meter. Calculation of discharge can be done using these equations. Experiment expected results. In open channel, the measured velocity will always vary across the channel section due to friction along the boundaries. This velocity distribution is not axisymmetric as in case of pipes due to the presence of the free surface. This is due to the presence of secondary currents circulating from the boundaries towards the section center and the resistance at the air/water interface. Thus, the velocity distribution is shown in the following figure. The vertical velocity distribution tends to have a max velocity just below the surface and to keep decreasing, reaching the velocity at the bed as shown. In addition, along the cross-section, the velocity distribution forms isovels equal velocity lines, as shown. Velocity tends to increase moving away from the boundaries. On the other hand, the velocity distribution method is a commonly method used to measure discharge. Thus, any difference between the calculated discharge and the measured discharge from the orifice meter should be due to measurement error or device problem.